Welcome back to the Deep Dive. We're here to unpack complex topics, distill those key insights, and really get you well-informed fast.
That's the plan.
And today, we're doing something a bit special. We're diving into a series focused entirely on helping you prepare for the CSWIP 3.1 Welding Inspector Exam.
Yep, a really crucial certification.
Absolutely. So our mission today is to tackle some common multi-choice questions, but it's not just about finding the right answer, is it?
No, not at all. It's about truly understanding the why behind it, the principles underneath.
Think of this as maybe a shortcut to mastering those critical welding concepts. Let's unpack this.
Right. And what's fascinating about these questions, they really go beyond just simple memorization. They properly test your grasp of, fundamental welding metallurgy, process control, defect mechanisms.
The core stuff.
The core stuff, exactly.
Yeah.
Understanding these principles isn't just about passing an exam, though that's important. It's absolutely crucial for effective inspection and, practical application out there in the field.
Real-world scenarios, basically.
Pretty much, yeah. Just in question form.
That's why we're here. So let's jump right in. Our first challenge is a really fundamental concept in welding, preheating.
Preheating, yes.
The question asks, select the correct statement from the following. And the options are A, preheating increases hardness, B, preheating increases cooling, C, preheating increases dilution, and D, preheating increases shrinkage stress.
Okay. This is a fantastic question because it really tests that core understanding. Preheating fundamentally is designed to mitigate several negative effects, not really increase them.
Right. It's a corrective measure almost.
Exactly. At its heart, preheating is about slowing down the cooling rate. That's key. Slowing the cooling of the weld itself, and crucially, the surrounding heat-affected zone, the HAZ.
HAZ, right.
It also helps reduce the thermal gradient, that sharp temperature difference between the hot weld area and the cooler base metal. And this is particularly vital for certain types of steel, like hardenable steels.
Okay, so if its main job is slowing cooling, that immediately makes me look sideways at option B.
Yeah.
Preheating increases cooling. That sounds, wrong.
It is. It's the exact opposite. Preheating is specifically designed to slow down cooling, like you said. Think of it maybe like taking a hot pan out of a warm oven versus taking it out of, say, a cold freezer. The temperature difference is much smaller in that warm oven scenario, right?
Much less of a shock.
Precisely. So the pan cools more slowly. This longer cooling time is really important metallurgically. It allows more favorable transformations to happen in the steel, preventing that rapid quenching effect that can lead to brittle microstructures. So B is definitely incorrect.
And following that logic, if it slows cooling, I'm guessing option A, preheating increases hardness, is probably also incorrect.
Yeah.
Because isn't fast cooling what usually creates hardness?
You're spot on. Exactly right. Rapid cooling, especially in those hardenable steels we mentioned, can lead to the formation of hard, brittle microstructures. Things like martensite in the HAZ.
Nasty stuff in the wrong place.
Definitely. So by slowing the cooling rate, preheating aims to reduce the formation of these unwanted phases, and thereby it reduces hardness and actually improves ductility. So A is also incorrect.
Okay, so it helps reduce hardness and it slows cooling. What about option C then? Preheating increases dilution. What's dilution again?
Dilution, yeah. It's basically the mixing of the base metal with the filler metal in the actual weld bead.
How much they blend together.
Exactly. And that's primarily influenced by things like your welding current, the voltage, travel speed, electrode stick out. Essentially, factors controlling how much base metal melts and mixes into that weld pool.
So the arc parameters mostly.
Right. Preheating's primary effects are thermal. It changes the starting temperature of the base metal before you even strike the arc. Now, while a warmer base metal might maybe subtly influence the fluidity of the weld pool, it doesn't really directly or significantly increase the compositional mixing, the dilution.
It's not its main job.
No.
Option D. Preheating increases shrinkage stress. Now, I always thought preheating was supposed to help reduce stress. Is that just me being optimistic?
No, not at all. You're absolutely right. Preheating generally reduces shrinkage stress. It definitely doesn't increase it.
Yes.
Think about it. As weld metal cools down, it shrinks, right? And this shrinkage can induce significant stresses, residual stresses, especially in joints that are heavily restrained.
Like thick plates or complex shapes.
Exactly. By preheating, you're ensuring a more uniform temperature distribution across the joint before you start welding. This reduces those steep thermal gradients we talked about.
Oh, okay.
So the weld and the surrounding metal cool more slowly and crucially, more uniformly together. This slower cooling also gives the material more time to deform plastically, sort of creep a little, which helps accommodate some of that shrinkage.
So it relaxes the stress a bit as it cools.
In a way, yes. It lowers the peak residual stresses that get locked in. So D is also an incorrect statement.
Okay. This is actually quite fascinating because it seems like all the options presented here are the exact opposite of what preheating actually achieves.
It does seem that way for this question, yes.
Which really highlights, for anyone preparing for the exam, how crucial it is to understand the why behind preheating. You can't just guess. It's about mitigating those negative effects, like excessive hardness, like high residual stress, by carefully controlling the cooling rate.
Precisely. Preheating is a preventative measure. It's designed proactively to improve the final mechanical properties and help avoid defects. It's a fundamental concept for a very good reason.
Okay, good start. Now that we've dug into managing those thermal aspects with preheating, let's pivot slightly. Let's look at the inherent characteristics, maybe the advantages of a specific welding process. Our next question focuses on metal gas arc shielded welding, MAG or MIG. It asks, what is one of the advantages of metal gas arc shielded welding? And the options are A, can be used in drafty locations without protection. B, produces a deposit low in hydrogen content. C, any welding position can be welded with spray transfer. And D, fine spatter at nozzle restricting gas flow.
Okay, lots to unpack there, but let's maybe cut right to the chase on this one. Option B produces a deposit low in hydrogen content. That is the key advantage among these choices.
Low hydrogen. Why is that so important?
Well, this is generally true for the solid wire MAG-MIG processes. And hydrogen is a huge concern in welding. It can lead to something called hydrogen-induced cracking or cold cracking.
Right, I've heard of that. Delayed cracking sometimes.
Exactly. It's a very dangerous defect because it can appear hours, even days after the welding is finished. Now, some processes that use flux, like maybe certain stick electrodes, shielded metal arc welding, stick
welding, yeah.
Right. Those can introduce hydrogen if the flux coating absorbs moisture from the air. But solid wire MAG-MIG uses, well, a solid wire electrode and an external shielding gas. Both of those are inherently very low in hydrogen potential.
Plus less hydrogen gets into the weld in the first place.
Exactly. Which significantly reduces the risk of those hydrogen-related defects in the final weld deposit. It's a major plus point.
That makes a lot of sense, especially given how serious hydrogen cracking can be. So what about the other options then? Let's look at A, can be used in drafty locations without protection. That sounds risky for something needing a gas shield.
It's not just risky, it's actually a significant disadvantage, not an advantage at all.
Oh, okay.
These gas-shielded processes rely completely on that protective blanket of shielding gas argon, CO2 mixtures to stop the atmosphere, oxygen and nitrogen, from contaminating the molten weld pool and the arc.
Right, needs to be pure.
Needs to be protected. Even a slight draft, a bit of wind, can blow that gas shield away. And if that happens, you get porosity, oxidation, nitrogen pickup, all sorts of serious weld defects.
So you need screens or something outdoors.
That's exactly why you often see screens or little tents being used when people are MAG-MIG welding outdoors or even just in breezy workshops. So A is definitely out. It's a limitation.
Okay, so you absolutely need that gas shield to be stable. Got it. What about option C? Any welding position can be welded with spray transfer. That sounds a bit too good to be true for spray transfer.
It absolutely is too good to be true. While MAG-MIG itself is very versatile, and it has different ways the metal transfers across the arc.
Different modes, yeah.
Different modes, right? Spray transfer mode specifically uses quite high currents, and it produces a very fluid, almost liquid weld pool. It's hot and runny.
Like pouring water almost.
A bit like that, yeah. And because that puddle is so fluid, gravity becomes a huge factor. This generally restricts spray transfer to flat positions, like welding downhand on a plate, or maybe horizontal fillet welds.
Where gravity helps you, or at least doesn't fight you.
Exactly. Trying to use spray transfer vertically, going up or overhead, the molten metal would just drip or fall out of the joint. You'd get a completely unacceptable weld.
So other modes for other positions.
Right. Other transfer modes like short circuit or pulsed spray are used for all position welding. But the question specifically says spray transfer. So C is incorrect.
Okay. And finally, option D. Fine spatter at nozzle restricting gas flow. I'm guessing spatter, whether it's fine or coarse, isn't usually seen as an advantage.
You're right again. Spatter is a pretty common characteristic of MIG welding, particularly if you're using pure CO2 as the shielding gas. It tends to create more spatter.
The little balls of metal that fly off.
Those are the ones. And while some process variations might produce finer spatter than others, spatter itself is generally considered a disadvantage. It means you have to spend time and money cleaning it off after welding.
Post-weld cleaning, yeah.
And more critically, like the option itself points out, that spatter can build up on the welding torch nozzle and the contact tip. If it builds up too much, it can actually obstruct the flow of the shielding gas.
Which defeats the whole purpose.
Exactly. Leading to poor shielding and potentially back to those defects like porosity we mentioned earlier. So D describes a problem, a potential issue, definitely not an advantage.
So when you really break down the nuances of the process, it's clear that producing that low hydrogen deposit really stands out as the significant advantage here among these choices, critical for weld integrity.
Precisely. It directly tackles one of the most insidious types of weld defects right from the start.
Okay, let's keep going. Our third deep dive takes us into the slightly scary world of welding defects themselves, specifically lamellar tearing.
Lamellar tearing, yes, a nasty one.
Definitely one you want to avoid. The question is, what is the primary cause of lamellar tearing in welding? And your options are A, excessive heat input during welding, B, poor through-thickness ductility in the steel plate, C, inadequate joint preparation, or D, use of a non-hydrogen-controlled welding process.
Right, lamellar tearing.
Yeah.
It's a very specific type of cracking. It doesn't happen in the weld metal itself, but in the base metal, usually just underneath the weld.
In the parent plate.
In the parent plate, exactly. You typically see it in heavily restrained joints. Think T-joints, corner joints, places where the plates can't easily move as the weld shrinks.
Lots of stress.
Lots of stress, particularly stress pulling through the thickness of one of the plates. And it has this very characteristic appearance, it looks like, steps or terraces running parallel to the rolling direction of the steel plate.
Okay, so that description helps visualize it. What's causing it then?
The primary cause, and this is really the key thing to grasp, is poor through-thickness ductility in the steel plate itself. That's option B.
Poor ductility through the thickness.
Yes. Think about how steel plate is made. It's rolled. During that rolling process, tiny non-metallic inclusions, things like manganese sulfides, silicates, they get elongated and flattened out.
Like stretching chewing gum.
A bit like that, yeah. And they end up oriented parallel to the surface of the plate. Now imagine you weld a joint, like a T-joint, where the weld cools and shrinks. That shrinkage pulls on the plate underneath, creating tensile stresses acting through the plate's thickness.
Perpendicular to those flattened inclusions.
Exactly. Those flattened inclusions now act like little planes of weakness. If the steel has poor ductility in that through-thickness direction, meaning it can't stretch much that way without breaking those stresses, can literally pull the steel apart along these planes of weakness.
Tearing it open like pages in a book.
That's a good analogy. It results in those characteristic step-like fractures of lamellar tearing.
Wow. That's fascinating how those tiny microscopic features, the inclusions, interact with the welding stresses to cause such a specific and damaging defect. It really hammers home the importance of knowing the material properties of the steel you're welding.
Absolutely critical. It's not just about the weld, it's about how the material responds.
So how do the other options fit in then? Could they maybe contribute, but they aren't the primary cause?
That's a good way to put it. The other factors can definitely cause welding problems, but they aren't the root cause of lamellar tearing's specific mechanism.
Okay.
Take option A, excessive heat input. High heat input can lead to larger grain sizes in the HAZ, potentially higher residual stresses overall, which might make tearing more likely if the material is susceptible.
But it doesn't create the susceptibility.
Exactly. It's not the fundamental cause. Then option C, inadequate joint preparation, poor fit up, wrong groove angle, that kind of thing. That can lead to all sorts of weld quality issues, lack of fusion, slag traps, uneven stress distribution.
General bad practice.
Right. But again, it's not the underlying material property issue that defines lamellar tearing.
Gotcha.
And finally, option D, use of a non-hydrogen controlled welding process. We already talked about hydrogen, didn't we?
Yeah, causing cold cracking.
Right. Hydrogen causes hydrogen-induced cracking or cold cracking. And while that's a very serious issue, it's a completely distinct defect mechanism from lamellar tearing. Hydrogen cracking is usually intergranular or transgranular, often in the HAZ or weld metal, and it's driven by hydrogen diffusion and stress. It's not directly related to those through thickness properties and inclusions in the same way lamellar tearing is.
So different causes, different appearances, different locations.
Totally different mechanisms, even though both are types of cracking.
So for lamellar tearing, it really boils down to the material's inherent weakness in that specific direction, the through thickness direction, being pulled on by the welding stresses. That's a really critical distinction for an inspector to make.
Absolutely. It's about knowing not just how to weld, but understanding what you're welding and identifying its specific vulnerabilities before you even start.
Right.